So let's use our LED. Click, 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 drag. Let's move this our C's blocking our view. Move it up. So click, drag, click, and connect. So positive to positive, negative to negative of the batteries. So let's run it. Perfect. So see that the LED is actually coming on now. It's on. So when A and B are both 1, the LED comes on. So if this were in real life, if we are to create this circuit in real life, we might not have a logic terminal that will be input and another logical terminal that will be output. If you don't have that, what you can just use batteries. Use two 5 volts batteries or two 5-volt DC sources. Combine two of them and then get an LED. You use 5-volt DC sources as your input and you use an LED for your output. So if you are to implement this in a physical laboratory, this is how you do it. If you don't have terminals for logic input terminals and logic output terminals, you just use DC source, a 5-volt DC source for your input and an LED for your output. Now, how do you vary your input? See that it's just permanently 1. We can vary it by using a switch. Go to input component, SPT switch, SPST rather. It means single pole, single throw switch, single pole, single throw switch. So we can use that switch to vary our input. We see here that A and B just permanently 1 when we use the DC sources, the DC 5-volt DC sources. So we can vary that. We can change the levels by, so just click and drag the switch. Click and drag the switch. So um you might have to you have to shift these batteries, or this so you have to shift them back a bit. Click on them, shift back. Okay, this is confusing. Delete. Click on them, delete. Click on the wires and delete. Right, click and delete. Left click and delete. Let's shift you can shift this A. Okay, so click and delete. Click and drag. Drag it. So click the switch, Ctrl C, Ctrl V. We can copy the switch, move the symbol S sub D1. So click connect one end of the switch to the gate, the other end of the switch connected to the battery, and then let's disconnect this one. Click and delete. Click connect. So the positive is going to the switch and the negative will connect them to each other. The negative of the DC sources or DC voltages are connected to each other, while the positives are connected to one end of the switch. The other end is connected to the gate. So now, when we simulate, you click on run, we see here that A and B are both 0, 0 because the switch is open. Now, when the switch is open like this, A and B are both 0, 0. They are both 0. If I click on it, this switch, bam, you see that it changes to 1. B changes to 1. A remains 0. Output C is 0. Click on it, is 0 again. So I'm confirming our earlier truth table. A is 1, B is 0. Now C still remains 0. Now let's do the last one when A and B is 1. You see that when A and B is 1, C is 1. So we are confirming it's the same truth table, the same circuit. The only difference is that we change the inputs from logical input terminals to 5 volts DC sources, and we change the output from output logic terminal, we change it to LED. So see here that when the switch is open, logic level is 0 because the 5-volt terminal is not connected to, we disconnected from, see, we can disconnect the 5 volts from the input, and that is logic 0. When we connect the 5 volts, when we close the switch, the 5-volt DC supply is connected to the corresponding input of the circuit, of the logic circuit or the logic gate, and that particular input is logic 1. And then the output is either logic 0 or logic 1, depending on the truth table and depending on the combination of the inputs A and B. So that is that about that. And we can see here that, so in the real practical sense, you use a DC source, make sure it is 5 volts, use that to generate your logic level 1. But you also need a way to disconnect it if you want to create a logic level 0. So you put a switch, so when you close the switch you have logic level 1, when you open the switch you have logic level 0. So this is how if this were a practical session, a physical laboratory, this is what we do. So let's get rid of it actually. um the whole point of the logic gate of this input is that it is small. Just one single terminal replaces the whole connection of battery to switch another input terminal. So it's because of the simplicity. They kind of they simplify the whole thing, the whole arrangement of having two DC sources and having two switches. They all simplify it to one terminal each. So for simplicity, for now, let's go back to this. So but just know that if you are to implement this in an actual sense, in a practical sense, or in a physical laboratory, and you don't have a input terminal somewhere, basically you won't get this input terminals are generated self. They are created by using 5 volts DC sources and switches. So I've just told you how to create inputs, logical inputs, and I've also taught you how to create logical outputs. Logical output, they use LEDs or bulbs, filament bulbs, to create logical output, and logical inputs are created by using 5 volts, um 5 volt sources, 5 volt DC sources and switches. Let's go to OR gate. So you've gone through the truth table for AND gate. So for OR gate, we want to go through OR gate. Let's delete our output. See, the input will still be the same. Remember that the input combination, these are all the possible combinations for two inputs, for two logical inputs to a circuit. So for, or let's click and drag. You click and drag the OR gate. You connect the OR gate where you connected the AND gate. So you want to determine the output if the circuit is, or if the logic gate is an is an OR gate. So let's start. Let's shift our B to over there, shift our A right over there, and so shift our A and B right there. And so we can fill up the truth table for all gates will be slightly different from that of AND gate. So when A and B are both 0, our output C is 0. When both are 0, the output is 0. And when B is 1, when B is 1 and A is 0, output C is 1. So we can fill that in. Output C is 1 when A is 0 and B is 1. Let's run the simulation once again. Now let's go to when A is 1 and B is 0. Then output C is 1. Run it again. When both A and B are 1, output C still remains 1. So we can see here that the output C will always be 1 unless both A and B are 0. So it's only when both A and B are 0 that the output of an OR gate is 0. So that is how it differs from an AND gate. So we've gone through an AND gate, now we've gone through the OR gate. So we understand the behavior of an OR gate now. We understand the behavior of an OR gate. So let's go to an inverter. Inverter is also called a NOT gate. It's also called NOT gate. So click and drag the inverter or the NOT gate. Click it and drag it. You want to understand its behavior. We've examined the behavior of an AND gate and an OR gate. So let's check one for a NOT gate, also called inverter. So let's insert another text box. We want to draw a mini truth table for NOT gate. A mini truth table for NOT gate, just a small one. So if you look at the NOT gate has only one input. So we can say maybe input A and only one output. We can call that output B. So um, unlike in the OR gate, A and B were both inputs and the output was C. But for the NOT gate, we made the input A and the output B. So Ctrl C, Ctrl V, change that to B. So let's copy and paste the input, copy the output terminal, paste, connect. So the NOT gate has one input and one output, and thus that's why the truth table just has A and B alone. So all the possible input for the input, all the possible entry for the input is either A is 0 or A is 1. That is all. So for a single input, you only have two possible combinations. It's either your input is 0 or 1, since it's only a single input. So if A is 1, let's see what happens. If A is 0, our B is 1. When A was 0, we saw that our B was 1. And let's see what happens when our A is 1. Run the simulation. When A is 1, our B is 0. So see here, what inverter does is that any input you give it, it would invert it, it would change it to the opposite. If you give it 1, it returns, it outputs 0 for you, and if you give it 0, it outputs 1. So the NOT gate is just an inverter, it inverts. So let's do that. Let's go back to our OR gate. So we've gone through the inverter. Let's check the NAND gate. Now if you look at that NAND gate, it's actually an AND gate with a small bubble in front. That bubble is a NOT. That bubble is an inverter. That small bubble in front of the AND gate is an inverter. So it inverts the what's supposed to be the normal outputs of. Okay, what did I do here? I think I've gone through a new window. This is a new window. Let me return back. Uh, okay, go to Windows Untitled. Yeah. So yeah. So I'm in the right window now. Okay. So the NAND gate is like the N in front of the NAND is not AND gate. So that NOT is that small bubble. That small bubble you have in front of the AND gate is the NOT. It inverts the normal behavior of an AND gate. So I can actually, even without that, I can predict the output of this NAND gate. I can predict the output. Normally, remember that a AND gate is supposed to be 0 1 1 1 1. So but it will be 1 0 0. It will invert it. The response will be different. So let's quickly run the experiment. When A is 1 and B is 0, their C is 1. And when both A and B are 1, C is 0. So see here, this is the opposite of a normal AND gate. For a normal AND gate, when both inputs are 1, the output will be 1. But for a NAND gate, not AND gate, that's NAND gate, when both inputs are 1, the output is 0. So it's opposite of AND gate. So opposite of AND gate is NAND gate. So we've got through a NAND gate. Let's go through the NOR gate. So NOR, just like NAND, NOR is not OR gate. So the NOR gate is an OR gate with a small NOT in front. So not OR gate. That's the full meaning of NOR. Not OR. So the small bubble in front of the OR gate. So that small bubble, it means that in a normal OR gate's behavior is inverted. The normal output of an OR gate is now inverted to give you uh, a NOR gate. So when both inputs are 0, the output is 1. Let's check. When B is 1, C is still 0. And when B is 0, sorry, when A is 1 and B is 0, C is 1. When both of them are 1, C still remains 0. So you see here that the output of a NOR gate is the opposite of the output of an OR gate. So the NOR gate, in a normal OR gate, when both inputs are 0, the output is 0. But for a NOR gate, when both inputs are 0, the output is 1, which is opposite. So the NOR gate is just created by putting a NOT gate in front of an OR gate. So next gate here is XOR. The X means exclusive, so it is exclusive OR gate. That's the full meaning of XOR. The full meaning of XOR is exclusive OR gate. So click and drag. Click on, let's delete the NOR gate. Click and replace. Connect the outputs, connect the inputs, connect them like so. So let's delete the, let's replace the output. The output will change. The output for an exclusive OR is different from the output of and OR gate. So let's run it. Now when both inputs are 0, the output is 0. When A and B are 0, uh, the output C is 0. So let's fill that in. 0, run. When B is 1, the output C is 1. And when A alone is 1, then the output C is also still 1. And let's see what happens when both A and B are 1. C becomes 0. So when both A and B are 1, the output C is sorry, not 1, is 0. The output C is 0. So we see here that for the exclusive OR gate, as long as either of the inputs is 1, the output will be 1. But when the inputs are the same, either both the inputs are both 1, or they are all 1s, or they are all 0s, the output will always be 0. So exclusive OR doesn't want repetition of inputs. The inputs have to be different. Once the inputs are exactly the same, an exclusive OR will have an output of 0 when the inputs are the same. Either the inputs are both 1 or the inputs are both 0. The output for both cases will be 0. So exclusive NOR gate is just a NOT gate. You put a small bubble in front of a normal exclusive OR gate. So that small NOT there, it will invert the normal output of an exclusive OR gate. So I can predict the output even without running the experiment. You see here that the output most likely will be 1 0 0 1, because normal exclusive OR gate is 0 1 1 0. By the time you put the bubble, the NOT in front of it, it will change. Where you have 0, it will invert it to 1, and when you have 1, it will invert it to 0. So you have 1 0 0 1 1 0 0. That I predict the output to be 1 0 0 1. It will invert 0 1 1 0. It will invert it to 1 0 0 1. So the exclusive NOR gate is basically an exclusive OR gate followed by a NOT gate that will invert the output of the exclusive OR gate. So let's connect the exclusive NOR gate. Let's connect them. Let's connect it rather. Exclusive NOR, X NOR, and let's delete the output. I predict it to be 1 0 0 1. So let's confirm whether my prediction will be right. So let's remove it, delete the output, and then we will run our virtual experiment. Now when A and B are 0, when A and B are 0, C is 1. Let's fill that in. 1. Now I predict the next value to be 0. So when B alone is 0, C is 0. When A alone is 0, when A is 1 rather, A alone is 1, C is 0. And when both A and B are 1, I predict the output to be 1. Yeah, so my prediction was right. So the exclusive NOR is just an exclusive OR gate followed by a NOT gate or an inverter. So we are done with OR gate, 2 input OR gates, 2 input AND gate, 2 inputs NOR gate, 2 input NAND gate, 2 input exclusive OR gate, and 2 input exclusive NOR gate. So you see there are so many other gates here apart from the ones we've examined so far. And probably we'll go through a couple of them before the end of today's lecture. And let's see, let's go to See here that there are three inputs AND gates, NAND gates, and there are two inputs AND gates. So there are gates that take in three inputs, and there are gates that take in two inputs. So you see here, this is a three input AND gate. Three input, so it takes in three inputs. So if you just drag and drop, we didn't see a three input AND gate in the standard gate. We had to go to the 7400 series to find a three input AND gate. So a AND gate, three input AND gate. So for a three input AND gate, our truth table will have to change, because a three input AND gate has three inputs. It's no longer two, it's now three inputs. So with the three inputs, the performance will change, the output will change. So let's move the our outputs ABC. Let's move them elsewhere. So now you see here that we've changed the input. C has now become input. C is now input. Control C, Control V. Connect A, connect B, connect C. So A, B, and C are now input. So it means that we need to create a new output now. We need to create a new output. Sorry. Control C, Control V, terminal. So let's change it now. This will now be D. Since A, B, and C are our inputs, that means you create a new output called D. So let's move that a bit. So this means that automatically our truth table will have to change. It can't just be so we have to add D. D was not in our truth table before, because we had two inputs before. Now that we have three inputs, our D will have to change, or rather our truth table will have to change. It has to be larger now. Our truth table will be larger than it was before. So we'll add D to it. Let's see. Let me see if I can adjust this truth table. Let me try and adjust it to take um, three inputs A, B, and C, and one single output D. So let's adjust that. Okay, let's make it as aligned as possible. And okay. Trying to align it. So 0, 0, 1, 0, and 1. I will explain how I came about the 0 1 0 1 0 1 for input C. I'll explain that later. B should be 0 0 and 1 1. 0 0 1 1, and this should be 0 and 0 0. So I want to try and fill up the total number of possible combinations for a 3 input circuit, or for a 3 input truth table. So let's drag this down a bit. Drag it down. Okay, so 4 zeros, 4 ones. Now if you look at it, if 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 you want to create all the possible combinations, possible input combinations for 3 digital inputs, the furthest one from the output, A is the farthest one, C is the closest input to the output, C is the closest one, followed by B, followed by A. So A is the farthest one. So the farthest one here, if it's 3 input, the farthest one will have 4 zeros and 4 ones. the next input, which is B, we have two zeros till two ones, so it is 0 0 1 1 0 0 1 1, two zeros, two ones. And then the closest input to the output, we have 1 0 1 1. So it's by a factor of 2 rather. Actually, the orders of the zeros and ones is by a factor of 2, or rather factor of 2 raised to power n, in that the farthest one has 4 zeros, 4 ones, the next one has 2 zeros, 2 ones, and then the closest input to the output, which is C, is 1 0 1 1. So at the end of the day, we have all the possible combinations for 3 inputs. Either all 3 inputs are 0, or one input is either all inputs A, B, C are 0, or only C is 0, or only B is 0, or only A is 0, or B and C. Sorry, let me take that again. It's either all 3 are 0. It's either A, B, C, they are all 0 and there is no 1, or only C. It's either all 3 are zeros, A, B, and C. It's either all 3s are zeros, all 3 inputs A, B, and C. Either they are all zeros, or only C is 1. Either A, B, and C. Either they are all zeros and there is no 1 there, or only C is 1 and A and B remain 0. That's another possible combination. Or only B is 1 and A and C remain 0. That's another possible combination. Or only A is 1 and B and C remain 0. That's another possible combination. So we've done all the combinations for the case where there is no 1 at all, and the case where there is only one single 1. And then another possible combination is where you now have two ones. When you have 1 in 2 places, 2 inputs are logic 1. So it's either B and C are both 1s, either B and C are both 1s and A remains 0, or A and C are both 1 and B remains 0. Is either A and C are both 1 and B remains 0, or A and B are 1s and C remains 0. So either A and B are both 1s and C remains 0. So we've gone through the case where there is no 1 at all. We've gone through the case where there is only one logic 1 among the inputs, and now we've gone through all the possible combinations of having 2 logic 1 inputs. Now the last possible combination is for all 3 inputs to be at logic 1. It's for all inputs to be at logic 1, A, B, and C being logic 1. So that is the last. So with this truth table down, there's no way you can arrange 3 logical inputs that this truth table doesn't reflect. This truth table reflects all the possible input combinations you can have for 3 inputs. So if you have an AND gate and you feed it 3 digital inputs A, B, C, all the possible combinations of inputs you can have, they are represented by this truth table, which has 3 inputs A, B, and C. So in order for us to get what the corresponding output will be for the various input combinations, we need to run the simulation. We'll run the simulation and then you will see what the output will be when we have the various corresponding input combinations. So like we said, you can probably I won't say you cram this, but you can probably there are various ways you can arrange, or you can determine all possible inputs for all possible combinations for 3 inputs. But the easiest way to do it is just to follow this procedure. Make sure that if you are drawing for 3 inputs, if you're doing a 3 input truth gate, that the input closest to the output, in this case which is C, would have zeros and 1 alternating each other. So 0 1 0 1 0 1 0 1 0 1, and then the next one to the closest one, that is B, the next one to the C, which is in this case is B, will now have 2 zeros and 2 1s. So that's 0 0 1 1 0 0 1 1, and then the next one, which is A in this case, will now have 4 zeros and 4 ones. Now if we had another output, if this were to be 4 output gates, if you had another output, then it would have been 8 zeros and 8 ones, but that's not for now, that's for another time. So let's start filling the truth table. When all 3 inputs are 0, the output D was 0. We run that simulation. Now let's run that simulation again. When only C is 0, D remains 1. D is 1 when only C is 0. So let's stop the simulation, press stop, and then when A is, sorry, let's do that again. Let's feed that in first of all. D is 0 when only C is 1. And then when only B is 1, D is also 0. When only A is 1, D is also 0. So let's go for 2 2 now. When B and C are 1, D remains 0. So we try that. When A and C are both 1, D remains 0. And when A and B are both 1, D still remains 0. So let's fill that in. 0 here, 0 here. For A and B being 1, D is 0. Now when A, B, C are all 1s, D now becomes 1. So D is 1 only when all 3 inputs are 1. So this is the behavior of a 3 input AND gate. This is the behavior of a 3 input AND gate. So let's go for NAND gate. NAND gate. NAND gate. A 3 input NAND gate. So let's drop and drag 3 input NAND gate. Drop and drag. Click. Click and drag. Click. Delete. So now we can create a 3 input NAND gate. If you don't want to use a 3 input NAND gate directly, you can actually create your own NAND gate. If you don't have a NAND gate and you have a NOT gate, you can create it by yourself. Just connect the output of a 3 input AND gate. Let's move the symbols. Let's move the labels. Click and drag it. You can move the labels on their own. So click the output of your AND gate. Click and drag. Click, click, click. So you can connect the output of your AND gate. Connect the output of your AND gate to a NOT gate, and then from a NOT gate to the output. So we've created our own 3 input NAND gate by connecting an AND gate to a NOT gate. So I can predict the output. Basically it will invert. This truth table is the truth table of an AND gate normally. So adding a NOT table will invert the output. So you're going to have, instead of 0 0 0 0 0 0 0 1, you're going to have 1 1 1 1 1 1 1 1 1 0. It's going to, when you have zeros, it will change it to ones, and when you have ones, it will change it to 0. So you're going to have 1 1 1 1 1 0. That's what they did not in front is going to invert the output. So let's delete and run the simulation and confirm for ourselves whether our hypothesis is right. So when A, B, and C are all zeros, okay, there's something wrong with this gate. It's giving us X in front instead of 1 or 0. So we might have to change the gate. It's another bug. 74LS10 doesn't want to work. Let's use another NOT gate. This particular NOT gate is misbehaving. So let's connect, click on it down, delete, okay, run. Perfect. Okay. Let's see. Let's get another AND gate. Another NOT gate rather. Delete this one. Run. Okay, this NOT gate also works too. Okay. So passive components, logic gates, inverter. Click